Welcome. Today we will discuss about an interesting topic for empirical estimation of your econometric model, that is logarithmic transformation of variables when you are estimating linear regression model. So, the topic of our discussion is logarithmic transformation in linear regression model. Okay. So far the econometric models what we were discussing, they were linear in nature. That means our model was like this: yi equals to alpha plus beta xi plus ui. Let us say that this is model 1, which is called linear model. Linear model. But sometimes when you work with data or when you read your textbook or some applied research paper, what you see that some of the variables, either independent or dependent variables, is transformed into log. And there are three alternative ways by which actually you can transform your model into a logarithmic transformation. You can either transform your independent variable x and keep y as it is, or you can transform your dependent variable y into log and keep x as it is, or you can transform both y and x in log form, right. So, there are three alternative possibilities, right. The second possibility, that means this is model number 1, where both y and x are linear, are unlog, that means they are not log transform. This is called linear model, right. The second model, let us say that yi equals to alpha plus beta log xi log of xi plus ui. This is, let us say, model 2, where we have transformed only x into log, and the name of this model is called Lin-log model. This is called Lin-log model. That means your left hand side is linear, right hand side you have transformed x into log, that is why it is called Lin-log model. Possibility 3 is this: log of yi equals to alpha plus beta xi plus ui, and this is, let us say, model 3, which is known as log linear model. Log linear model, right. And possibility 4 is log of yi equals to alpha plus beta log of xi plus ui. This is possibility 4, which is called log model, or sometimes it is known as double log model. Now, depending on which particular functional form you assume for your regression model, interpretation of beta will change. So, in today's objective of my today's lecture is to make you understand two things. First of all, why do you require this logarithmic transformation? And secondly, what would be the interpretation of your beta hat if you estimate model 1, model 2, model 3 and model 4. So, interpretation of beta hat is different in these 4 alternative models, and that is what we are going to learn. So, let us first try to understand why logarithmic transformation is required in empirical research. So, why logarithmic transformation? Why logarithmic transformation is required? There are several reasons. I will discuss one by one. First reason is, what happens sometimes your dependent variable y and independent variable x, they have some kind of nonlinear relationship, and we have not yet learned nonlinear estimation technique. So, we need to somehow linearize that apparently looking nonlinearity between y and x, so that we can actually apply linear regression technique estimation to estimate your beta hat. Okay? What I am saying? Sometimes your dependent variable y is non-linearly dependent with your x. How is this? Let us say that your yi equals to 1 by 1 plus e to the power minus alpha minus beta xi. This is your model. So, you can easily see that y and x, they are non-linearly dependent, and we have not yet learned nonlinear estimation. So, what we will do? We can linearize this model by logarithmic transformation. How to do it? Let us say that we are doing this yi divided by 1 minus yi equals to 1 minus 1 by 1 plus e to the power minus alpha plus beta xi. Okay? And that means this would become e to the power minus alpha plus beta xi. So, you can easily solve this. So, what will happen? It would become e to the power minus alpha plus beta xi. I am not doing all the steps. Okay? E to the power, sorry, it would become e to the power alpha plus beta xi, right. And then if you take log of this yi divided by 1 minus yi, it would become alpha plus beta xi. Okay. So, when your yi and xi, they are non-linearly dependent, then yi by 1 minus yi, you can easily understand that you can calculate 1 minus yi first, then you divide this, divide yi by 1 minus yi, and you will get e to the power alpha plus beta xi, and then if you take log, it would become log of yi by 1 minus yi equals to alpha plus beta xi. You can add the error term, stochastic error term here, then you can easily estimate this model using linear estimation technique. Okay. So, that means one reason for logarithmic transformation is to overcome the nonlinearity between your yi and xi. So, I will write shortly when yi is non-linearly dependent on xi. Log transformation makes the model linear. Okay? This is one reason. Second reason, reason 2. Sometimes we see that your y variable, dependent variable or some of your independent variables are highly skewed, okay, highly skewed. So, sometimes either yi or xi exhibits highly skewed distribution. For example, let us say that you are estimating a consumption function, and if you look at where consumption is a function of several variables, okay, you are estimating a consumption function, and if you plot the histogram of that consumption data, then what you will see, this is let us say histogram of consumption or expenditure data, weekly or monthly expenditure. So, what you will see that this is let us say 0, and then this is 0, then 500, then 1,000, like that it is having. So, there would be huge data here, and then in this range, and then you see this type of distribution. Okay. So, that means your distribution is like this. So, this data is left skewed, it is left skewed, and for our estimates to be unbiased and efficient, what we want that they should exhibit some kind of normal distribution. Okay. And if you transform this expenditure into log, and then if you plot the log expenditure here, then your expenditure, the histogram will look like this. So, that means it will be more or less normal, which is called a log normal distribution. So, that means the distribution becomes normal after logarithmic transformation. So, this is another reason when you are either dependent variable or independent variable, they are highly skewed in nature. So, that means there are too few observations with higher value or too few observations with lower value, then the distribution is either left skewed or right skewed. So, what you do, you transform the variable into logarithmic transformation, and then what you see that your log norm, the resultant distribution of the log transform variable shows more or less the normal distribution, which is known as log normal distribution in the literature. Okay. So, these are the mainly two reasons for which we can transform our variable into either the dependent or independent variable into log transformation. There are another reason, sometimes you see that some of your independent variable, because of their unit, some of the independent variables variables have high magnitude because of their unit. Okay. For example, you are measuring, let us say your x1 is monthly income or yearly income measured by rupee, and you have another variable which is, let us say, family size. Okay. So, x1 will give you value like 1 lakh, where the family size is only 5. Okay. Family size is only 5. So, if you include this type of variables, because of their unit, some variables shows high magnitude and some variables is so very low magnitude because of their unit. So, you can transform the variable like income, expenditure, this so on and so forth into log transformation, so that you can get a parity in terms of their magnitude of all the explanatory variables in the model. These are the some reasons for which this logarithmic transformation. And when we transform the variables into log, please keep in mind that here we consider natural log. Here we are considering natural log with base E equals to 2.718128, something like that. Okay. Or you can say that this is 2.72, roughly 2.72. This is the natural log we are considering here with a base E, and some of the important properties of logarithm would be useful to understand the interpretation of your beta hat. Some important properties: properties of log. First of all, since we are considering natural log which is base E, we can say that log of E equals to 1. Secondly, log of 1 equals to 0. Thirdly, log of A base E equals to A. Then fourth, log of x to the power r equals to r log x. These are the important properties. And then fifth, log of a b equals to log a plus log b and vice versa. then log of a by b equals to log a minus log b. These are the some important properties of logarithm that we are going to use here. So, we have understood why logarithmic transformation is required and some of the important properties. We are going to use natural logarithm for our purpose. Now, we will take all those 4 models one by one and then we will try to interpret the beta hat. So, model number 1, which is a linear model, yi equals to alpha plus beta xi plus ui. This is the linear model, and what is the interpretation of beta hat from this model? As we all know, for a unit change in xi, expected value of yi changes by beta hat amount. This is the interpretation we know so far. We have learned this. For a unit change in xi, on an average or the expected value of yi changes by beta hat amount. Now, we will take our second model, which is basically, what was our second model? If we go back, our second model was this: yi is in linear form, but we have transformed x into logarithmic transformation. So, yi equals to alpha plus beta log of xi plus ui. So, we need to understand the interpretation of beta hat from this model. Okay. Now, if you apply the interpretation of beta hat from model 1, then what we can write? For a unit change, I am not doing anything, I am just replicating the interpretation of beta hat from model 1 into model 2. So, what will happen? For a unit change in, instead of xi, I am saying log xi, because my independent variable is now xi. For a unit change in log xi, expected value of yi changes by beta hat amount. Okay, beta hat amount. But if you say that for a unit change in log of xi, understanding this interpretation becomes little difficult, because what we want for a unit change in xi, we can easily understand the change in x, but understanding one unit change in log x becomes little difficult. So, we will convert this interpretation into a unit change in xi. How to do this? So, when I am saying that for a unit change in xi, let us say that log x is increased by 1 unit. So, log x, if it is increased by 1 unit, it will become log xi plus 1. Okay? This is 1 unit change in log xi. This we can write as log of xi plus log of e. From the properties we have discussed earlier, that log e equals to 1, and this we can write easily as log of e into xi. Okay, e into xi. This is also another property, log a plus log b equals to log of ab. Okay, so that means what we can write, that when log xi is actually increased by 1 unit, that basically means that your x is multiplied by e. So that means it implies that x is multiplied by e, which is equals to 2.72. Okay. So, 1 unit change in log xi implies 1 unit, that means ultimately what I can write, that 1 unit change in log xi implies 2.72 minus 1 into 100 percentage change in x. So that means we can say that 172 percentage change in xi. Please try to understand what I am saying. First I said that what is the interpretation of beta hat? For a unit change in log xi, yi changes by beta hat amount, that is what we are putting here. So, for a unit change in xi, expected value of, for a unit change in log of xi, expected value of yi changes by beta hat amount. Now, 1 unit increase in log xi is nothing but log of xi plus 1, which is log xi plus log e. Okay, log xi plus log e, and that is nothing but, that means I am saying that 1 unit change in increment in log xi is nothing but multiplying x by e, which is equals to 2.72. Now, if you convert this into proportional percentage change, that is nothing but then 2.72 minus 1 into 100, which is nothing but 172 change. So, that means what does beta hat indicate here in this model? When x changes by 172 percentage, that means ultimately what we got, when x I changes by 172 percentage, expected value, expected yi changes by beta hat amount. But this is also something difficult to understand. Why? That means I am saying when xi changes by 172 percentage, this is something this is not very comfortable for us to understand. Rather, what we want, some smaller percentage change in xi. Let us say when x changes by p percentage, when x changes by p percentage, we can use the result of this and say that when x changes by p percentage, expected value of yi, expected yi changes by beta hat into log of p plus 100 by p, okay, p plus 100 by p percentage. So, that means if you say that let us say p is 10, there is a 10% change in x, okay. So, this implies when x changes by let us say 10%, expected yi changes by beta hat into, if you put a 10 here, 110 by 100, that means log of 1.1, okay. So, equals to beta hat into let us say log of 1.1 equals to 0.095 percentage, okay. For small p, for very small p, this log of p plus 100 divided by 100, okay, is actually equivalent to p by 100, okay, p by 100. So, that means let us say for example, when p equals to 1, that means we are saying there is 1% change in x. When p equals to 1, expected value yi changes by beta hat divided by 100, okay, beta hat divided by 100 percentage, okay, right. That means let us say after estimating your model, this is your model, yi equals to alpha plus beta log xi plus ui, and you estimated beta hat equals to let us say 0.50. This is your estimated beta hat, okay. So, what is the interpretation? For 1 unit change in x, expected value will change by beta hat divided by 100, okay, beta hat divided by 100. So, that means this would become 0.05%, okay. So, this is how we can understand the interpretation of beta hat when your independent variable is transformed into logarithm, okay, logarithmic transformation. Sorry, this is not percentage, this is not percentage, this is unit. This is not percentage, okay, beta hat, this one. So, for a unit change in, for 1% change in xi, expected yi will change by your beta hat divided by 100. That is what you have to understand.